in this example, we can start with the usual guess. We assume that y is just e to the something t, let's say e to the rt. And then using that guess, what would the characteristic quadratic look like?
I'm not sure.
Well, with our guess, if we want to check if that guess actually works, we can fill in the guess and its derivative and second derivative into the original differential equation. Because usually if you want to check whether a guess actually works, you just fill it back into the original differential equation, see if it makes the equation true. So of course, that means we'll need the first derivative and the second derivative. Each one just bringing out an extra times r from the chain rule. So if we fill those in, y double prime can be replaced with r squared u to the rt. Plus 6 times y prime. But we know y prime can be replaced with r e to the rt. Plus 9 times y, and y is just our guess itself, e to the rt. And we want to know, does that really equal 0? And it seems at least possible for this to add up to 0 because we've got something e to the rt plus something e to the rt plus something e to the rt. But since e to the rt shows up in every single one of those, what can we do with that?
You could pull it out, right?
Yeah,
So
we
then,
can factor out that e to the rt. We're left with r squared plus 6r plus 9. And if we've got this quadratic times e to the rt equals 0, well, could equal 0. We're trying to check if it does. One of those two multipliers has to be 0 in order for the product to be 0. Is e to the rt ever going to be 0?
no.
So we can ignore that since that's never going to be 0. Instead, we need this piece to be 0. So this is what we call the characteristic quadratic, r squared plus 6r plus 9. That's the characteristic quadratic of the original differential equation in the sense that it's a quadratic that tells us everything we need to know about this differential equation. And you can generally jump from the original differential equation directly to the quadratic as long as it's in the form something y double prime plus something y prime plus something y equals 0, as long as those coefficients are all just constants. In such a case, you can always guess y equals e to the rt, and you'll always just end up with the y term being the constant, the y prime term being the linear term, r, and the y double prime term becoming the quadratic term, the r squared. Any questions on that setup so far?
No, I don't think so.
So now that we have the characteristic quadratic, can you solve that quadratic for r?
Yeah, is it r equals -3 and -3, or?
Yeah, because this one factors to r plus 3 times r plus 3. So we just get r equals -3, and that's it. In many cases, we would expect a quadratic to have two solutions. So we, like if the solutions were, let's say, 2 and 5, we'd end up with e to the 2t and e to the 5t. In this case, though, we just get one solution, e to the -3t. So that's our solution. Let's call that y1. y1 equals e to the -3t. The problem is, for a second order differential equation, we should expect two categories of solutions, usually called y1 and y2. So if we had gotten two values for r, we would have e to the r1t and e to the r2t. And then our general solution would be linear combinations of those, where C1 and C2 are arbitrary constants, which could be determined later by the specific solutions. But we can't just have another copy of e to the -3t because we need a genuinely different solution. If you just have two copies of the same solution, you may as well combine them with as like terms, and then you just have c times a single function. So we need one more solution. Any questions on that so far?
No. But since there's r plus 3 and r plus 3, can we just say they're both -3, or can you not do that?
Well, the problem is if we try having like y equals c1 e to the -3t plus C2 times another copy of e to the negative 3t.
Oh, I see. And then
Yeah,
if
the
you plug
problem is
in,
those end up being just combined. You just get C1 plus C2 times e to the negative 3t. And then C1 plus C2 is just another constant.
oh, okay.
But for second order, you're going to have two pieces of information for the initial conditions. So you need two free variables in order to make that work out as a system of equations. It's not going to do it with just one free variable.
Yeah, okay.
So to get one more type of function, there are several different ways to accomplish getting this one more type of function. I think that possibly the most common method and perhaps the most applicable to other situations is called reduction of order. Reduction of order is a technique where if you already have one solution, it allows you to find the other solution to the second order differential equation. The reason it's called reduction of order is we make a certain guess that allows us to turn the second order equation into a new, simpler first order equation, reducing the order of the equation. And then we can solve that first order equation. The typical guess is if you're given y1, that is one solution, you make the guess that y2, because we know that any scalar multiplier of y1 will be a solution. We're going to make the guess that the other type of solution is some unknown function. Let's say some function v times y1, where v is an as yet unknown function of t. In practice, it turns out that v is just whatever multiplier will turn y1 into another solution y2. So for instance, if y1 is e to the negative 3t, and let's say y2 turns out to be like cosine of t, then v is going to be the multiplier that turns y1 into y2. Specifically, it'll be e to the positive 3t times cosine of t, because that multiplier will cancel out the e to the negative 3t and introduce a cosine of t. Of course, that's not what y2 is going to turn out to be here. But in general, no matter what the functions are, there's some multiplier that will turn one of them into the other. And our goal here is to find that multiplier so we can figure out what y2 is. Any questions on that so far?
No, I don't. So you don't have to use cosine, correct? That was just an example.
Right, that was just one possible function. It's not going to be the actual solution here. But I'm just trying to make the point that no matter what the two functions are, no matter how different they seem, there will always be some function, some multiplier that will turn one function into the other.
Okay.
No matter how outlandishly different they are.
Okay.
The idea is once we make this guess, we guess that y2 is some unknown function times the solution we've already got. So let me make a note of that off to the side. In this case, so in general, we're going to guess that y2 is some unknown function times y1. In this particular case, that means our guess for y2 is some unknown function v times e to the negative 3t specifically. And as before, how do we check whether a guess actually works or not?
Would you plug it back into the original equation?
Right. Which of course means we're going to need y prime and y double prime as well.
Mm-hmm.
So to find y2 prime, we're going to need to take the derivative of this. Since it's a function times a function, how do we take that derivative?
Use a chain rule, maybe? No, I'm not sure.
For any function, for any product of functions, we can use the product rule to find the derivative.
Okay.
The idea that the derivative of fg is f prime g plus g prime f. So we can take derivative of the first thing times the second thing exactly as is, plus the first thing exactly as is times the derivative of the second thing, which will bring out a -3 due to the chain rule. So that'll become -3 times v times e to the negative 3t. So this will be the first derivative. And then the second derivative, we'll need to apply the product rule to each of these terms individually. The first one, we take the derivative of the first thing, v prime becomes v double prime. And then first thing as is times derivative of the second thing, that brings out a -3, so we get -3 v prime times e to the negative 3t. And then for this next term, we've got a -3. So we take the derivative of the first part, the v, that becomes -3v prime e to the -3t exactly as is. And then the first part as is, -3v times derivative of the second part. Derivative of e to the -3t brings out another -3. So -3 times -3 becomes +9v e to the -3t. Any questions on those derivatives so far?
No.
And also, these two terms have the same v prime and e to the -3t, so we can combine those. This just becomes -6v prime e to the -3t, from the -3 and -3 combined. And lastly, the +9v e to the -3t. So that's our y2 double prime, the second derivative of our guess. Fill that in up here. V double prime e to the -3t minus 6v single prime e to the -3t plus 9v e to the -3t. So with the guess and its derivative and second derivative, we can now fill that into the original differential equation and figure out what v has to be to make that true. So let's try that. Going back to the original differential equation, y double prime is going to be this whole thing. Plus 6 times y prime. So that'll be 6 times the entire first derivative. And I'm just going to multiply 6 by each of these terms. So 6 times the first term is 6v prime e to the -3t. 6 times the second term would be -18v e to the -3t. And lastly, we also have plus 9 times the original function. So 9 times v e to the -3t. And we want those to all equal 0. So when we're combining all those together, is there anything that can combine or cancel out easily?
Can the -6v prime e to the -3t cancel out the other +6?
Yeah, those are just going to cancel out to 0 easily. Anything else?
And then you could add the two 9s and then subtract it from the 18, and those will cancel out.
Yeah, 9 plus 9 plus -18 reduces to 0. So it looks like all that remains is v double prime e to the -3t has to equal 0. And of course, the e to the -3t is never going to be 0. So we're left with v double prime has to equal 0. In other words, the only way this guess will work, and it will work, but the only way it works is if v is a function whose second derivative is 0. So now that gives us some information about v. It still looks like it's second order, but since it's just v double prime equals 0, how could you get rid of one of those derivatives?
Can you find the antiderivative? Or...
Yeah, we can just take the antiderivative, the integral of both sides with respect to t. That cancels out one of the derivatives, so we're left with v single prime equals, and integral of 0 is just 0 plus a constant, because we want to be sure we're including all possible solutions. Let's say C3, because we're already using C1 and C2 in the general solution. So that means v has to be some function whose second derivative is 0, which means its first derivative is just a constant. This is where the reduction of order comes in. We've rewritten it as just a first order equation. And then we can also solve that first order equation. In some cases, it may be a more complicated first order equation, but still solvable using the techniques from chapter 2, either separation of variables or possibly integrating factors if it's linear. In this case, though, we can just take the derivative or take the antiderivative again. Integrate both sides of this with respect to t. On the left side, integral and derivative cancel out, so we just have v equals. And then on the right side, what's the integral of C3?
Would it just be like a C4 or will it still be C3? Or
Well,
will
it's
it
a
be
constant.
C?
What's the integral of any constant with respect to t? That is, what's a function whose derivative is a constant?
I don't know.
It might help to think of this as having a t to the 0 attached to it. If you think of this as C3 times t to the 0, what happens when you integrate t to a power?
The power will increase and you put it over a number.
Right. So if you increase the power by 1, you get t to the 1.
Yeah.
In other words, C3 times t.
Oh.
Because the derivative of C3t would just be C3. And also, since we're looking for all possible solutions, we should include plus some other constant, let's say C4. But ultimately, this just tells us, in this case, v has to be a linear function, something t plus something. And you could go through the same procedure with any solution, as long as you've got one solution of the original differential equation. Even if it's not in the format of e to the something t, this same procedure should work in general, as long as you've got some sort of linear differential equation, even if the coefficients are not constants, even if the coefficients are functions of t. As long as you know one of the solutions, maybe it's given, or maybe you find it by trial and error, this method of reduction of order, where you guess that the second solution is some unknown function times the solution you've already got, fill that in, and you should end up with at least the v terms canceling out. So you get just v prime and v double prime, or possibly even just v double prime. And then you can turn that into a first order equation and solve for v.
Okay.
So now that we have v in this case, let's see what the actual solution is going to look like. We now know y2, since we were assuming y2 can be written as v times y1. We found that v has to be a linear function. C3t times e to the negative 3t plus C4 times e to the negative 3t, because we can distribute the e to the negative 3t to both terms. So this is what we get for y2. However, we're just going to be filling this in the general solution anyway. All we're going to do is take this whole thing and multiply by C2. So we'd end up with some constant times t e to the negative 3t plus some constant times e to the negative 3t. But we already have some constant times e to the negative 3t. That was just y1. We don't really need to include that a second time. That's just going to combine with y1 anyway, so we can leave that out. But this t to the negative 3t, that's a genuinely new type of function. So that's really what we want to include. Or to put it another way, you could choose any C3 and C4 you want, because we're just going to be multiplying by constants anyway. The e to the negative 3t doesn't provide any new information we don't already have, so I would just set C4 equal to 0. We want to keep this new type of function though, so let's set C3 equal to 1. That gives us, in simplified form, y2 equals t times e to the negative 3t. That's a genuinely different type of function than e to the negative 3t. So we can use that for y2. And in general, anytime you've got a differential equation with constant coefficients that has a repeated root, so you only get one type of solution from the e to the rt, the other solution in general is going to be t e to the rt. The extra times t multiplier doesn't change the fact that it's a solution, as long as it's a repeated root situation. And it ends up being a different type of solution.
Okay.
So our general solution is going to look like C1 e to the negative 3t plus C2 t e to the negative 3t. So that should cover all possible solutions. Any questions on that so far?
No.
And you mentioned the Wronskian earlier.
Yeah.
Sorry, were you saying something?
Yeah, sorry. So you said that for any repeated roots case, so like since we had one for y1 where the roots was -3, it'll always, the y2 would always be t to whatever e to the variable you got for y1.
Yeah, as long as the characteristic quadratic results in only one solution, like a repeated root, then you'd have e to the rt as one of the solutions, and then t e to the rt should work for the other solution. And you can go through all these steps again, but it's going to lead to the same result anyway.
Okay. Oh, that's why it's called repeated roots. Okay.
And I would recommend going through all the steps on at least a couple of examples just to get a feel for why it works. And to verify that it really does work in all these situations. But once you get the hang of it, you can generally jump directly from, oh, it's a repeated root, to then this will be the other solution.
Okay.
And then of course that only works for repeated roots. If your quadratic leads to two different roots, then you'd have e to the r1t and e to the r2t, and there would be no need for this. In fact, this wouldn't work if it's not a repeated root situation.
Okay, so if we have to use a quadratic equation, it wouldn't be considered a repeated root case?
Well, the quadratic formula can lead to repeated roots. It just, if you go back to, I mean, the quadratic formula can be used to solve any quadratic. When would this lead to only one number instead of two numbers?
I don't know.
Or to put it another way, what's the only part of the quadratic formula that results in two different numbers anyway?
Is it the square root? Or...
Yeah, because we've got plus or minus this square root. We have -b plus the square root value and -b minus the square root value. What's the only value where it doesn't matter whether you're adding or subtracting it?
The 2a part? Or
I mean, what's the only possible value of this where it doesn't matter if you're adding this value or subtracting this value? What's a number that you could add or subtract and still get the same result?
Is it 1 or 0?
It's got to be 0. Adding 1 and subtracting 1 give you different value, but adding 0 and subtracting 0 give you the same value. So going back to the quadratic formula, if b squared minus 4ac happens to be 0, then you get this result. That is, this happens if b squared happens to equal 4 times a times c. For example, in this case, b squared would be 36. 4 times 1 times 9 is also 36. So if you didn't notice in the first place that this is factorable as a repeated root, you could use the quadratic formula. You're just going to end up with the discriminant being 0. So you just get -b over 2a, and that's it.
Okay.
So that's another thing to look for. If you're not sure whether it leads to repeated roots, check the discriminant. Check b squared and check 4ac. If they're the same value, then this becomes 0, so you get a repeated root.
Oh, okay. Cool.
Any other questions on that so far?
No. I think I'm good.
And you mentioned the Wronskian earlier. What do you know about the Wronskian so far?
So far, I just know that you have to use some type of linear algebra. But that's noticeably all I got from it.
The main idea of the Wronskian is checking if the two solutions you found are really enough information to cover all possible specific solutions. Because if you wanted to actually find a specific solution, if you want values for C1 and C2, what information do you need in order to find C1 and C2?
Do you need initial values?
Right. So the initial conditions in a second order equation would be of the form knowing the y value at a certain time and also knowing the slope, the y prime value at a certain time. So let's say y of 0 is some value y naught, and y prime of 0 is some other value, let's say v naught. Since if y represents position, the first derivative would represent velocity. So let's assume we know the starting position and starting speed of the object, assuming this is talking about an object moving around as time passes. If we wanted to write out equations to find that specific solution, we would write our general solution, let's say C1 y1 plus C2 y2. set that equal to y naught. And we're assuming we're filling in 0 for t, so let me fill that in. And then for the other initial condition, we'll need to take the derivative. So we get c1 y1 prime plus c2 y2 prime. Fill in 0 for t, or whatever the initial condition is, usually 0, but it doesn't have to be. And set that equal to v naught. So we get a system of equations because y1 of 0, y2 of 0, y1 prime of 0, y2 prime of 0, those are all just going to be some number. But c1 and c2 are unknown variables that we're trying to find. We could use linear algebra to write this system of equations as a matrix equation. Our matrix of coefficients times a variable vector, c1 and c2 being the variables we're trying to find. And what are the coefficients that we're multiplying by c1 and c2?
Is it y1 and y1 prime, and then y2 and y2 prime?
Yeah. Because that way, if you multiply rows and columns, you get c1 y1 plus c2 y2, c1 y1 plus c2 y2 equals y0, y naught. And likewise, this row in this column, c1 y1 prime plus c2 y2 prime, and c1 y1 prime plus c2 y2 prime has to equal v0, the starting speed. So the system of equations we get from the initial conditions can be turned into one matrix equation. And ideally, we want this initial conditions to lead to one c1 value and one c2 value. We want a unique solution. And we want the solution to exist in the first place. What has to be true about this coefficient matrix in order to guarantee that there's a solution and only one solution?
I don't know.
Let me write this in a little more abstract way. Let's say you've got, let's call this matrix capital Y, and this vector C. And this, the initial conditions, let's call that y naught vector. We want to solve for vector C. Is there any way you could just get rid of matrix Y and get C equals something?
Yes, you divide the big Y by y naught.
You can't divide by a matrix though, but what is the equivalent of dividing by a matrix? What could you multiply by that acts like getting rid of it?
The inverse?
Yeah.
Okay.
If we take y times c equals y naught, if we multiply both sides by the inverse, big Y inverse on both sides, then on the left side, y inverse times y becomes the identity matrix, times c is just c, equals big Y inverse times y naught, which means there will be a solution and only one solution, since there's only one result you can get from multiplying these together. However, that only works if big Y has an inverse in the first place. So this solution is unique. This solution exists and is unique if and only if big Y, that is this coefficient matrix, y1, y2, y1 prime, y2 prime, is invertible. So that's the conditions that need to be met. Notice it doesn't, that this restriction, this requirement doesn't depend on the initial conditions at all. It just depends on y1 and y2, the solutions we chose for a general solution. So as long as y1 and y2 and y1 prime and y2 prime make this matrix invertible, that means we should be able to get a unique solution no matter what the initial conditions are. And how do you check whether a matrix is invertible or not? What's usually the fastest way to verify that? Do you remember a list from linear algebra, a list of statements that are equivalent to this matrix is invertible? Let me send you a link. I've got a website that has a list of these. You go to math.ancheese.org/m22a/non-singular.html. That's got a list of many statements that are logically equivalent to this matrix is invertible. So if any one of those is true, then the matrix is invertible. And which one of those do you think would be easiest to check?
Would it be the second one where A has an inverse A -1 such that?
Well, that's what we're trying to verify. We're trying to check,
Oh.
does this matrix have an inverse? We could try finding the inverse, but that would probably be a lot of trouble.
Yeah.
But typically the easiest one on this list to check if we have values for everything in the matrix is the determinant. If you find the determinant of this matrix and it happens to be 0, that means the matrix is not invertible. But we want the matrix to be invertible, so we need to check that the determinant is non-zero. So that's typically what we do here. We take this coefficient matrix, y1, y2, y1 prime, y2 prime, and take the determinant of that. That determinant is called the Wronskian determinant. Or sometimes just the Wronskian for short. It's usually written as W of y1 and y2. The idea being we're taking two functions as input, and we're taking the determinant of this matrix, y1, y2, y1 prime, y2 prime. And you can expand this to more functions as well. If you're dealing with a third order equation, you'd have 3 types of functions as solutions. So you'd have y1, y2, y3, y1 prime, y2 prime, y3 prime. And you'd also need a third row because you can only take the determinant of a square matrix. So the third row would be the second derivatives, y1 double prime, y2 double prime, y3 double prime. So you can extend this to any size you want, any number of functions. But for second order, we'll just need 2 solutions. So to find that determinant, for any 2x2 determinant, 3x3 and larger gets more complicated, but for a 2x2, you can just use the shortcut and multiply across the diagonals and subtract. So first diagonal, y1, y2 prime, minus second diagonal, y1 prime times y2. So that value, whatever you get there, is the Wronskian determinant of those 2 functions. And as long as that is non-zero, then that means the original matrix is invertible, which means you really do have enough information there. So let's try that out in this case. In this situation, we're looking for the Wronskian determinant of these 2 functions, e to the negative 3t and t e to the negative 3t. So e to the negative 3t, t e to the negative 3t. Derivative of e to the negative 3t would be negative 3 e to the negative 3t. And then derivative of t e to the negative 3t, we can use the product rule again. T derivative becomes 1. So we just get 1 e to the negative 3t plus first thing exactly as is times derivative of the second thing. Gets a negative 3 from the product rule, or sorry, chain rule. So negative 3 e to the negative 3t times t. So this is the determinant we'd be taking to find the Wronskian of these 2 functions. So we got, again, y1, y2, y1 prime, y2 prime. And again, to evaluate the determinant, we can multiply across the diagonals. So e to the negative 3t times all this. We can distribute that. E to the negative 3t times e to the negative 3t minus 3t e to the negative 3 times e to the negative 3t. And then subtract the other diagonal. T e to the negative 3t times negative 3 e to the negative 3t becomes plus 3t e to the negative 3t. Wait, we're multiplying e to the negative 3t times e to the negative 3t, so that's actually negative 6t. When we simplify that, what's going to happen?
The 3's will go away and you'll just end up with e to the negative 6t.
Right. Is that ever going to be 0?
No.
So that is never 0. The fact that the determinant is never 0 means, yes, this matrix is invertible, which means we get a unique solution. And that's good. That means these 2 functions really are enough. And in terms of linear algebra, we would say these 2 functions are linearly independent. In general, if the Wronskian of y1 and y2 is not 0, then we'd say y1 and y2 are linearly independent functions. Whereas if the Wronskian happened to be zero, exactly zero, then that would tell you that they're not really different functions, that one of the functions is just some multiple of the other function in disguise. And that would mean you don't have enough information. You would genuinely need a different type of function to be y2. In this case, though, this y1 and this y2 lead to a Wronskian being non-zero, which means they really are different types of functions. They're linearly independent. And that tells us that this general solution will work, that this general solution should apply no matter what the initial conditions are.
Okay.
Any other questions on that?
Say if we messed up with, like, say with the general solution and we do get it where it is equal to zero, would that tell us that we messed up, or would that be like?
It would essentially tell you that you don't really have two different functions.
Okay.
Like, for instance, earlier we were talking about e to the negative 3t. You can't just have another copy of e to the negative 3t.
Yeah.
Ultimately, the mathematical reason for that is if you did try having e to the negative 3t and another copy of e to the negative 3t, when you take the Wronskian, if you just had e to the negative 3t and another copy of e to the negative 3t, then negative 3 e to the negative 3t and another copy of negative 3 e to the negative 3t. The Wronskian, the determinant of that matrix, would be zero. It's not invertible because it's got that repeated column.
Oh, okay.
So that would tell you that those aren't really different solutions. You need to go back and find another second solution that is genuinely different.
Okay.
That's ultimately what the Wronskian is checking. The Wronskian is checking, do these two functions provide genuinely different information, or is one of them just a copy of the information that the other one already provides? We want uniqueness here. We want no redundancy. We want each function to provide information that the other one couldn't provide on its own.
Okay.
All right, I've got to go get ready for my next workshop, but try this approach on some other differential equation as well. Once you've got two solutions, try finding the Wronskian and verify that the Wronskian is not zero.
Great. Awesome.
So give that a try, and I will see you next time.
All right. Thank you.
You're welcome.